That's great. So, I'm going to make a start then. Today, thank you for everyone for joining. We have David Morissette here talking to us about the uncertainty in biomeasurements. He'll go into a bit more detail about that, but I just want to please remind everyone that the thoughts and opinions are that of the speaker and not the IFE or the IFE Southern Branch. If you have any questions, can you please put them in the chat section or the Q&A box just at the bottom of the screen, and we'll ask them to David at the end. So over to you, David. Thank you.
All right, thank you very much. You still hear me okay? Excellent, perfect. All right, well, hello everyone. Thank you for attending today. My name is David Morissette. I'm a PhD student at the University of Edinburgh, currently supervised by Dr. Angus Law and Dr. Roy Haddon. I want to start by thanking the IFE Southern Branch for inviting me here to speak today. I'm excited to present on this topic. I'd be very interested in having a continued dialogue about this presentation afterwards, so I'll be sure to leave some good time for Q&A at the end for some discussion, or I'll leave my contact details for anyone who'd be interested in sort of following up on this topic offline. But today I'm going to be speaking a little bit about this sort of broad idea of uncertainty, in particular uncertainty in fire safety engineering, and how we as fire safety engineers can consider the concept of uncertainty in the analysis that we might be doing. So I'll be breaking down some of these terms of what I mean by uncertainty and how we might be able to address specific uncertainties. And instead of viewing them as sort of this unknown and sort of an idea of a question mark behind what does this uncertainty actually mean, we can actually use it as a tool to sort of articulate our confidence in a specific analysis. So before we get too far in, just a little bit about me. Before I started my PhD, I spent a little bit of time as an FPE consultant in the United States. And then I spent a brief period of time working as a fire safety engineer in Melbourne, Australia as well. So now I'm working on my PhD. I'm in my final year of my PhD. And in particular, I've spent a lot of time doing experimental research in the lab. And so getting involved in a range of different sort of laboratory projects sort of gives you a different perspective, I guess, on how some of these uncertainties sort of work their way into some of the calculations and the analysis that we might do as fire safety engineers. So for any tool, any calculation, any model that we might sort of use as a fire safety engineer, there will be inherent uncertainties to them. So understanding these uncertainties and being able to effectively articulate them gives us an idea of how to express our confidence in any analysis that we might do. So the goal of this presentation is pretty straightforward, hopefully. It's to highlight the uncertainty and limitations of common tools that we use in fire engineering, right? So I'm sure there'll be a broad sort of background of people in the audience today in terms of what the day-to-day looks like, in terms of what kind of analysis we might be doing as engineers. But I know at least from my experience, when using certain tools or calculation methods, there wasn't that much time where we sort of dedicated to looking at our analysis and saying, oh, well, actually, I wonder how much uncertainty I have in this calculation, right? You know, if there's a calculation method we would use, the output would be the output largely. Without too much discussion around, you know, what is our confidence, you know, in the inputs that we're using for this calculation, right? So the whole goal of this presentation is to look at uncertainty as a tool to which we can convey our confidence, right, in a given analysis. And then the rest of the presentation will be in particular examples of specific bits of analysis that we can actually sort of quantify and articulate this uncertainty in. So let's go through some examples of fire safety engineering calculations and how uncertainty might play a role in those kinds of calculations. So starting from the viewpoint of particularly a UK regulatory context, let's start with BS 7974, which outlines a wide range of calculation methods that we might use as fire safety engineers. So whether you're looking for trying to approximate radiation from a fire to a target source, or you're trying to look at the temperature distributions in something like a ceiling jet after a fire plume, this is the kind of document where you could start and sort of look at for some of those kind of calculation methods. Now, in this document, section 4.1 introduces this idea of uncertainty, stating that the complexity of the interactions between people, buildings, and fire, coupled with the gaps in knowledge, means that there will be a degree of uncertainty associated with fire safety design. And so part of the designer's role is to identify these uncertainties and adequately mitigate any associated risks, right? So essentially, the role of the designer, or our role as fire safety engineers, is to be able to identify the concepts of uncertainty and be able to articulate how these uncertainties propagate into the outputs that we then use in analysis. So just to go through a couple quick examples that are outlined in BS 7974, these are just a few examples of some of the calculations that we might use as fire engineers. Maybe characterizing fire growth, for example, something using like an alpha t squared fire as sort of an input to additional analysis. What kind of uncertainties might be able to propagate into this? What's our assumed growth rate? Things like that. Or we might look at things like ceiling jet correlations, right? If we were trying to calculate the temperature distribution in a ceiling jet, what kind of uncertainties might propagate into the inputs that we might use for this? How much confidence can we place in the output of these calculations? Or perhaps something like, what is the fire size required to flash over a compartment, right? And this is actually an example that we'll go into some specific detail in later slides. But the idea, again, being this sort of a simple relationship by which we can sort of get a single output of this is, the output of this analysis, but to what degree can we put confidence in that? And we're going to go through a few of these in specific detail. But things like these kinds of correlations and these kinds of calculation methods aren't the only kind of analysis that we might do. I'm sure a lot of people spend time doing things like CFD modeling, right? So when looking at the inputs to something like a CFD model or a two-zone model or different analysis like a FEM modeling or looking at taking temperature distributions and looking at the structural response of a structural member, how much certainty can we place in the inputs of that analysis and how does that propagate to the outputs? So the idea today is to go through sort of two course categories of fire engineering tools, right? We'll focus one on what we'll call simple correlations or correlations in simple models. And in particular, I'll be going through the example of flashover correlations. And these are the kinds of things that you might see presented in codes and literature. But in particular, we'll be looking at flashover. And the second category being largely what we'll call complex analysis, such as what are the inputs that we use for something like a CFD model, right? And in particular, we'll be looking at the variability in heat release rate data as an input to additional analysis, right? And everything I'm presenting today are tools that I've used in some capacity as with some experience as an engineer. And then I've also had the opportunity to now sort of get a little bit of a research perspective in terms of from laboratory experiments. And so now hopefully this is sort of an intersection between the use of these tools as an engineer, but also a little bit of experience looking at it from sort of uncertainty and research perspective. So the first idea that we're going to start with is correlations in simple models, right? And so things like correlations are very easy to recognize if you know what to look for. Essentially, most often you'll see a very simple sort of relationship as seen here, where you have a series of inputs and then they're linked to an output calculated value. And then they're linked together by a constant that is nested within the correlation, which is generally calibrated from experimental data. So if you take a look at just this correlation on its own, without the data, then you don't fully capture the context behind the correlation itself, right? And so this is just a simple example of a correlation. It was correlated by McCaffrey. It's the temperature rise under a ceiling from a fire plume as a function of this dimensionless group. But essentially, the actual formulation isn't important. In this instance, it's just the idea that we have calculation methods where there's simple inputs, single output, right? But if you look at that, there's a degree of scatter around this correlation, right? This is the actual experimental data that was used to correlate the data. Correlate the actual functional relationship, but there is an inherent sort of degree of uncertainty or error bars around this correlation. So this is just one example. And so if you recall some of the examples that I referenced from BS 7974, there are other kinds of correlations that we might come across, right? So now let's actually look at this degree of scatter around some of these correlations. Let's try to quantify something like an error bar on one of these correlations. And today we'll be focusing on the concept of flashover in terms of this correlation. And I'm sure many people here are very familiar with the concept of flashover, but flashover is that sort of proverbial transition from a room in a fire, a fire in a room to a room on fire, right? And what that means is basically you go from a localized fire, usually a single item or a few fuel packages burning, and then based on the ventilation conditions of the room, you eventually transition to a point where all of the fuel in the room has ignited. And so the process of flashover is controlled by this complex interplay between the ventilation conditions and the development of a smoke layer, which acts to heat the remaining fuel in the compartment. And we won't go into too much detail about the interplay of all these different phenomena, but on a simple level, we can say because flashover is linked to this idea of ventilation, you are able to then predict the onset of flashover by identifying this ventilation factor. Now, the benefit of the ventilation factor is that this is based on the geometry of the compartment alone. It has nothing to do with the fire inside the compartment or the fuel inside the compartment. It is purely a function of the openings of the compartment, right? And so this is a useful tool in sort of in correlating the onset of this flashover. And the output that we're going to be looking at is we like to sort of look at this threshold flashover using the fire size, right? So that's, again, the heat release rate, probably terminology that many people are familiar with. It's your fire size, right? It's the rate of energy release. It's in units of power. It's the kilowatts, megawatts of the fire. And so there are simple correlations that exist that correlate the onset of flashover in terms of a heat release rate to this ventilation factor. One of which is the correlation presented by Bobrowskis, as seen here as a simple sort of linear relationship between your ventilation factor and the heat release rate at flashover. You also have the MQH correlation, a very similar formulation. You see the ventilation factor nested in it with a few other terms, and you have the Thomas correlation. Again, you see in each case, you see the ventilation factor sort of cropping up in the correlations themselves. And so I've used the Bobrowski correlation, for example, in a few projects in the US and Australia. Also, the MQH and the Thomas correlation are both referenced in BS 7974 as potential methods for looking at the flashover potential of a compartment. Now, irrespective of the differences between the correlations, right? Let's just look at, for example, the Bobrowski correlation alone. Just looking at this correlation, right? You can theoretically put a single input into this and get a single output, but looking at the equation on its own doesn't give us any fundamental insight really into what's my level of confidence in this output, right? I have one input, I get one output, right? But what are my error bars on that? Do we have an idea of what the range might be? What limit do I have on putting a ventilation factor in here to begin with? Can I use this for all size compartments? Is there only a certain range of compartment sizes I can use this for? So these kind of questions start to crop up as we start looking more and more into these equations. So let's break down the Bobrowski's correlation a little bit in detail. So to dig into this a little bit more, I'll be focusing again on just the Bobrowski's correlation. But you can start by extracting the original data from the original publication. Here you can see the heat release rate as a function of ventilation factor and the nice linear relationship between them, right? So let's start by extracting that data and replotting it. And just note that this is now replotted on a non-logged basis. So just sort of the more physical intuition behind what do these fire sizes actually mean. And as a point of reference, 1,000 kilowatts, right? So 1 megawatt, these data points here, that's sort of like, for a rough order of magnitude, for anyone who might not be immediately familiar with that, that's something like the peak heat release rate of something like an upholstered couch or something like that, right? Just very rough orders of magnitude, but that's the kind of fire that we're talking about, right? Now, if we look at the correlation, we do see a nice linear relationship between the ventilation factor and your flashover heat release rate. And with that linear relationship, there is a degree of scatter around the correlation, just like we saw for that correlation previously. Now, in theory, we could plug in a single value, right, a single ventilation factor, and get a single output from this correlation. Very deterministically, single input, this is the value I would get from this calculation, right? But now what's interesting to note is if we had done that, for example, a ventilation factor of 3, in this case, the correlation would overpredict the heat release rate at flashover compared to what was experimentally determined in one of these experiments. So that's interesting in this context in particular, because if we're overpredicting our heat release rate flashover, then that means we'll actually reach this in a growth rate sooner in reality than we would actually be predicting with the correlation. Therefore, it could be an unconservative analysis, right? So there is some need to which we should be able to put error bars on these kinds of correlations. And then with that, we can maybe articulate how much confidence can I place in a single calculation, right? So let's address this for this correlation. Now, I'm going to break up the idea of uncertainties into sort of 2 categories, right? So the first category that we have, we'll look at statistical variation, right? These are the error bars I've been talking about, right? So as we can see, there's a degree of scatter around this correlation, and this can be calculated by taking a regression analysis of the data in the correlation and taking a 95% confidence interval between the difference of the data and the correlation itself, right? So in other words, with 95% confidence, we can put these error bars around the correlation and say that our original correlation has a plus or minus of about, say, 520 kilowatts with 95% confidence, right? Now, there's multiple different ways that we can articulate these error bars, but this is just one approach to it. But the benefit of this is that we say with the data, we can start to say these are the bounds of values that we might expect based upon the experimental data. So we can actually start to articulate confidence in this calculation, right? And so that's the error bars. This is sort of the second part of this uncertainty to look at. It's worth noting that this correlation was only determined over a certain range of ventilation factors, right? So in theory, we have no idea what happens beyond the data that was actually collected, right? While there might be a physical basis to extrapolate this beyond, the ventilation factors that were experimented, without the data to back it up, the correlation is only as good as the range of values that we've used to create the correlation. And so we have no idea what's going to happen afterwards without the data to back it up, right? So the whole idea is to look at this is the range of ventilation factors that we can actually apply to this particular correlation, right? So together, we had this sort of calculated error bar, the calculated scatter on our actual correlation, and we can pair that with a range of applicability, right? And these are two very simple approaches to sort of now we can actually start to articulate. Instead of just looking at this equation in isolation, we can now better contextualize what is my confidence in the output of these kinds of equations. What are the range of values I can actually even use this for, right? And by sort of digging into the original correlation, we can actually start to articulate these ideas a little better. But let's not stop there, right? So that's just the Bobrowski's correlation. But you remember there was 3 other flashover correlations that we briefly discussed that we could use in an application like this, right? So without going into a regression analysis for each one of these, let's just quickly look at how do all 3 of these sort of stack up to one another if we want to plot this on top of the data that we're looking at here. So recall that each of these correlations are fairly similar. There's a ventilation factor that's nested in here somewhere that gives you the heat release rate at flashover, right? Now, and then there's a few other terms in here which effectively come down to they represent heat losses to the boundary of the compartment. But basically the only difference between the original Bobrowski's correlation, which is just linking the ventilation factor to the heat release rate at flashover, is we need to make an assumption about the size of the compartment for these other ones, right, to get the areas of the compartment. And so if we take this figure here, and we're looking again at heat release rate at flashover to the ventilation factor, we can take the original data that we took from the Bobrowski's correlation. We can then put the Bobrowski's correlation over it. And then let's start playing around with what does the MQH correlation look like for a 3 by 3 by 3 meter compartment, for example. And this is what the correlation would produce, right? So similar sort of general behaviors, but you have a different functional relationship between the ventilation factor and your heat release rate at flashover. Still capturing quite a bit of the data, but if you were to put error bars on this, the error bars would look different, right? What about the Thomas correlation for something like a 3 by 3 by 3 meter compartment? That's what the correlation would look like, right? But what if we wanted to go same ventilation factor range, but we wanted to go bigger compartments? Let's say the MQH for a 5 by 5 by 5 meter compartment, or Thomas for the same size compartment. And very quickly, we start to sort of have to ask ourselves, which is the one that I want to use for my analysis, right? And to be honest, I don't actually fully know the answers to those questions necessarily, but there's something to sort of keep in mind when there are multiple options for calculating these values. It is worth taking a moment to go back to the original correlations to see, okay, is one of these meant for a different range of values than another one, right? Can we actually use these two in the same exact scenarios? What are our range of applicabilities between these different models? What are our error bars on these different models? And these are kind of questions that aren't immediately apparent in a lot of the sort of codes and standards that sort of reference these equations. But it's something to sort of keep in the back of our minds of being able to articulate the confidence in those outputs will be different between the different models that we use. So just to quickly, again, going back to sort of the Bobrowski's correlation in particular, because that's the one that we've calculated the error bars for. Let's sort of recap where we're at with that, right? So with 95% confidence, we can put error bars on this. Now, if I want to use this equation, I can say it's plus or minus blank, right? And we can use it within a range of, say 0 to 3.4 for a ventilation factor. Again, just to sort of give some physical intuition behind what do these numbers actually look like. Something like a ventilation factor of about 1 is more or less a single door opening, right? So for a compartment with a single door opening, we're looking at a flashover heat release rate of about 1 megawatt, right? So recall that's sort of the peak heat release rate for something like an upholstered couch or something of that kind of fuel package. But then on the other end of the range of applicability for this correlation, now we go up to about a 2 by approximately 1.25 meter, right? These are sort of approximate figures here, but this opening is more like, let's say, on the order of a double door, right? And that's the kind of range that we can go to with this correlation, right? That's the confidence level that we have, right? If we start extrapolating too far beyond that, now we're making an extrapolation. The same level of confidence cannot necessarily be applied to that without higher resolution in our data, right? So the combination again of the error bars and that range of applicability allows us to start being able to actually like articulate the confidence that we can place in that calculation, right? And this idea can extend beyond just this correlation, right? Again, every calculation method that we can do, these two principles still apply. Can we get error bars on our calculations? And do we know the limits to which we can apply this kind of calculation? And so in sort of talking is particularly about the range of applicability, let's put aside the mathematics for a second. And it's worth taking a moment and talking about, if we're looking at flashover, right? We're looking at this, transition to ventilation limited conditions. What kind of compartments are we looking at, right? Can this be applied in any instance, I guess is the question, right? So are we talking about compartments that look like this? Or are we talking about compartments that look like this, right? Because a fire that develops in these two different compartments could develop very differently, right? And so this concept of flashover is most closely linked to the kinds of fires that we would call regime one fires, your sort of ventilation controlled fires, which is described in a lot more detail in the compartment fire dynamics literature. But not to say that you can't get localized ventilation limited conditions in large open spaces, right? There's plenty of examples where we can see things like flashover like phenomena in large spaces. But let's go back to what we've been discussing. We've been discussing a very specific tool, right? And that's the flashover correlation, which has largely been developed for these sort of boxy, sort of regime one, smaller type compartment fires, right? So the whole concept of the correlation is applying it within the realm of applicability that we're looking at, right? And so just because you can take the equation, and we could, in theory, put in any ventilation factor, right? So there's nothing stopping me from taking that equation and calculating the heat release rate required to flash over a stadium, right, or an atrium, or very large spaces where the physics of the process of flashover no longer fully align with the calculation method itself, right? So beyond just looking at the graph and the data, right, it's also worth taking a second to look phenomenologically speaking. Are we within sort of the realm of what we think this correlation should be used for, right? And that applies again to any sort of calculation method we might be using. So that was, we'll say, our simple correlations, right? Simple inputs, simple outputs, right? So very deterministic, so to speak. Now let's move on to something that's a little more complex, right? So what do our uncertainties look like when we are trying to put input data into things like complex calculations like CFD modeling, zone modeling, evacuation modeling? The list can go on. But these complex models require a range of input parameters, right? And so naturally, like the reliability and the accuracy of our model outputs, are going to be based on our confidence in our input data. And so one of the key inputs to this kind of analysis, like CFD modeling or two-zone modeling, is generally you have to choose something like a heat release rate, right? And this isn't the only thing you have to choose for something like these kinds of modeling applications, but this is generally the heart of our design fire analysis, right? Many design fires are going to be based around the concept of the heat release rate. What is our fire size? How is that fire size growing? What's our maximum fire size? And all these things have so the heat release rate has many knock-on effects to many different calculation methods that we might use. So recall to those calculations that we saw in BS 7974, right? So whether it's our ability to actually define the characteristic fire growth curve, or looking at things like ceiling jet correlations, or again, our flashover correlations, all of these have the heat release rate nested in there somewhere, right? So the heat release rate is an integral part of all sorts of applications, such as these correlations, but also it's an integral part of, again, something like a CFD model, right? And so defining particularly our transient development of that heat release rate, right? How does it start? How does it grow? What's our maximum fire size? All those have significant implications to things like our modeling outputs, right? And so if we're to choose a heat release rate to use in a certain application, we ultimately need to decide what is the design fire that I want to represent this particular scenario with. So our selection of a heat release rate effectively tells us this is the fire that I think is most appropriate for this scenario, right? And so in choosing a heat release rate curve, you broadly speaking have sort of two categories to choose from. We can use these sort of idealized type fire curves. So you see here, you see an alpha t squared growth curve up to a peak heat release rate, and then a decay curve, right? Now what you see here is a very sort of general fire curve, not very specific to any specific experiment. And so what you make up for what you lose in sort of specificity, you make up in sort of general applicability. But on the other end of the spectrum, you could use the input data from a real experiment, right? This is the actual heat release rate curve of burning a single seat, sort of upholstered chair underneath a calorimetry hood, right? So this is the transient development of the fire over time. And you can see sort of jagged peaks and troughs throughout the experiment, which represent sort of transient aspects of fire growth and decay. But what you don't get sort of a more general characteristic curve when you look at real data. Now, whether we're using real experimental data or we're looking at sort of generalized fire curves based on assumed alphas and assumed peak heat release rates, generally both of these scenarios end up making their way back to the concept of experimental data. Even the alphas that we use or the peak heat release rates that we assume, sometimes like the sort of ballpark numbers that we use, like the 5 megawatt fire, that's sort of a gold standard in certain applications. All those come back to experiments that were conducted at some point, right? And sort of this idea of these are the kind of fuel packages that we're looking at, right? So running these experiments gives us an idea of how big of a fire we should be expecting, and it helps sort of inform our design fire metrics. So let's take a quick look at if we wanted to get real heat release rate data for a fuel package, what does that look like, right? How does this process work, right? So we can actually get the heat release rate of a complex fuel package, let's say, and this is in this instance this 3-seater couch, and we put it beneath a calorimetry hood, and we light it up. We want to see how is this going to burn underneath this hood. So as the fire develops, you can actually determine the transient fire growth over time. So this is the heat release rate curve over time, which gives you the idea of how big the fire grows and how it decays as a function of time. And so this captures the transient behavior and of the fire size of this fuel package. And then we can use this as an input to things like we saw for, let's say, calculating ceiling jet temperatures, or again, take this directly and put it into something like a CFD model, right, if we wanted to. And the power of looking at the heat release rate experimentally is we're able to make these sort of ideas of how big of a fire might we expect for a specific fuel package, right? I could take anything I want, I could put it underneath the hood, I can light it up, and we can see what that kind of fire is going to look like, right? And then we can use that to then inform design fires, assuming that you have similar fuel packages in your compartment. Now, this is where the tricky part comes in, though, right? And so while this is very powerful, and this gives us the ability to say, this is the kind of fire that we might expect, what happens if I had ignited the couch in a different position, right? What if I had, say, oriented the couch differently? What if I had added more pillows to the couch? I mean, all these different variables start stacking up. Are we going to get the same heat release rate output? Right. If I was to preheat the couch, for example, assuming a sort of compartment fire dynamic sort of scenario of a smoke layer heating the couch, how does that change the heat release rate? If I'm putting this in my compartment, will it behave like this, or will it behave slightly differently? All these become very interesting questions. And one question that I was particularly interested in myself was, if we're going to characterize the fuel this way, if I took this experiment and I just ran it again, right? How much confidence in the same exact scenarios, how much confidence do we have that it's going to follow this exact curve again, right? If this is the output that we're going to be looking at, how much confidence do we have in that, right? And so that's something that we looked into a little bit. So going off that idea, here are two identical experiments that were presented in the SFB handbook for, I believe they're for wardrobe fires. And let's say you took this first experiment here, seeing this gray curve, and you see a peak heat release rate of around 100, 120 kilowatts. And let's say that was the only experiment that we had conducted. And we say, that's my characteristic design fire for this fuel package. right? But just by running that same experiment again, now you see a peak heat release rate of somewhere upwards of 200 kilowatts, right? So almost twice the peak heat release rate for the same fuel package in the same sort of configuration, right? So this idea of if we just gone with our single data point, right, we wouldn't know there actually is a possibility of having almost twice the peak heat release rate in a different fire scenario, right? So looking at this sort of variability, how does that apply to something like the heat release rate of a single upholstered chair? Right? This is a single seater, very simple sort of upholstered chair that we burned in our lab. And this is just the curve that comes out of it. But what happens if I took that same exact chair in the same scenario and I wanted to ignite it again, right? Because if I'm going to inform my design fires based upon this fuel package, and again, some people, I think people out there might be thinking, and very rightly so, this isn't necessarily the largest fire you might use as a design fire, right? So it's true. Maybe I don't want to use this exact chair. It's a good point. But if we can extend this logic to any fuel package, right? So say this is a three-seater couch, right? If I ran my experiment and this is the output, how confident are we that we can get that same output again, right? And what are our error bars in that kind of analysis? Right? And there's not too much work in the literature on that for this scale of fuel packages. Generally, if we're looking at repeat experiments, we only see upwards of say 3 experiments repeated. And so what we wanted to do is we wanted to go higher than that. So we ended up taking the same fuel package and we ran it 25 times over and over again, same conditions to look at what does the variability look like. And so we ended up, again, running a total of 25 experiments. These are just a few of them on the same upholstered chair with a small Bunsen burner igniting the chair from beneath. And again, these are only a few of the trials, but as you watch these side by side, it becomes apparent that the fire behavior is different between these different scenarios, right? Some of these are already getting up to their peak heat release rate, while some of them are slowly just still growing in their heat release rate. So visually, you can start to see these differences between these different experiments, and that just becomes more and more apparent as time goes on. Right? Some of them start mechanically failing, right? Because these are actual upholstered chairs, and these all occur at different times, right? So just by actually observing these side by side, you see same fuel package, same ignition conditions, same experimental configuration, and there are differences over the course of time. Right? Now, this is the results of the heat release rate curves of all 25 repeat experiments of the same item underneath our calorimetry hood under same exact experimental conditions, right? And something that I really like about this figure, and I like to ask people whenever I show people this figure is this more or less repeatable than you would expect if I told you that I was going to take an upholstered chair and burn it 25 times, right? I think it's a really interesting question, and I'll be curious to maybe hear a few responses in the Q&A afterwards. But if you ask many people in fire were like, actually, I see some general trends, right? That's actually, it's kind of impressive. But if you show this to someone who's, say, a biomedical researcher, right, they'd be appalled at this being repeatable, right? But it is what it is, right? This is what the data show. And so I think it's fair to say that there is a degree of variability. You can see, for example, there's quite a different range of growth rates of the fire. If you take any instant in time, let's say 500 seconds into this experiment, you have anything from a 50 kilowatt fire to a 250 kilowatt fire, right? So on a time basis, there is quite a degree of variability here, right? But equally, I can also see that there is some commonality across these experiments. There is sure different growth rates, but you have a growth up to the peak heat release rate somewhere here, and then a decay down to at the end when the chair breaks down. It's just a sort of smoldering pile of mess. And so while there are distinct differences in time, you can start to see there maybe are some commonalities between the experiments, right? And so how do we start putting things like error bars on this is the hard part. And so we'll get into that. So I think one important thing to take away from this figure on the right is to show that this is the same data, but this is the range of all the data, the interquartile range, and a median, right? So take a look at this median value here. So it's sort of a common practice in sort of experimental work. If you take multiple experiments, generally people want to take some sort of average of those data, right? But what's interesting is if we look at all this data in time and we take just a median or effectively an average of the data in time, this median curve no longer really represents any of the individual curves seen over here, right? If you look at the peak heat release rate of the median, you get something like 160 kilowatts, right? But if you look over at the original data, any individual curve had a peak heat release rate of upwards of 200 or 250 kilowatts, right? So, and the reason for this is sort of obvious as you start to look at it more. It's because all of these peaks are occurring at different times, right? So these are no longer synced with one another. So if you take an average in time, you're truncating your peak significantly, which again is sort of intuitive once you acknowledge that. But this is still a practice that many scientists do, and this is sort of the easy approach. If we take multiple data points, I'm just going to take an average through them, right? And something we don't necessarily think about in every instance. But something that, like I said, a really important takeaway is if we're looking at inputs for our analysis, for example, looking at things like multiple heat release rate curves, then it's important to keep in mind that maybe an average through the data is not the best way to go, right? And because you're going to start getting things like a truncation as peak value, because this heat release rate as an input to our analysis would not necessarily be characteristic of our data, right? And then all this becomes a little bit clearer as we start looking at the data a little closer. Now here we have the same data, but let's focus on two individual trials, right? So again, all 25 trials of the heat release rate curves and two individual trials are sort of highlighted here individually. So it's the same chair, same ignition procedure, just different outputs, right? Different results. And one thing that's interesting to note right away is you get sort of similar peak heat release rates, right? But the time at which you get to the peak is very different, right? Which means that your growth rates to that peak are going to be different between these two cases, right? If you were looking at this from sort of a alpha t squared sort of perspective, your alpha values are going to vary quite a bit. And looking at the data set as a whole, you have alphas that range from sort of the fast sort of growth rates all the way to sort of a slow growth rate from terms of the standard alpha values that you might choose. And so there are, again, significant differences in the time result data between these two cases, right? You can see that becomes very clear, but sorry, you can start to make sense of these differences though if we actually link these occurrences not to the time itself, but if we actually identify key events that occur over the course of the experiment. Because the heat release rate is just the manifestation of how this chair happened to burn, right? It is linked to all these physical occurrences that happen over the course of the experiment. So instead, by just observing the experiment and marking these key events, we can actually contextualize these results a lot closer. So if you see up here, there's a few key events that we identified. At event number 1, we've removed the burner. So about 2 minutes into the experiment, we remove the burner. The fire breaks through the top of the seat cushion and starts spreading along the seat cushion, right? This is a characteristic of a relatively low period of fire growth. But right when we reach event number 2, when the backrest of the chair ignites, now all of a sudden we've switched to an upward flame spread regime. So now the flames rapidly race up the back seat of the chair. And in both cases, we get a rapid increase in the heat release rate. It just occurs at different times. So the same result occurs across both trials, that rapid sort of acceleration in the heat release rate. It just occurs at different times between the trials. But by linking it to the occurrence of that event, we can start to sort of see commonality between the experiments. And that goes on to when the flames reach the top of the chair, we see a period of relatively steady fire growth again. And then again, the last event is when flames break through the backseat of the chair. We get, again, a rapid acceleration to a peak heat release rate. And all of these are occurring at different times across the two trials. But if we sort of, in your mind's eye, start to drag those events on top of one another, we start to see commonality between these two very different trials in time, right? So looking at them in time, you lose some of the context of what's actually driving this process. What are the physical events that are occurring that's causing these differences? So by identifying the key physical drivers of this burning process, we can actually better contextualize this, what looks like a very different result in time actually turns out to be driven by the same phenomenon, right? So we can become, I guess in other words, we can say, I'm not so confident saying I can predict the exact heat release rate as a function of time. But I do have quite a bit of confidence now in saying that once this backrest ignites, I can tell you a range of growth rates at which you're going to get to the next event, right? And so from a physical understanding, that gives us a lot of insight into how complex fuel packages burn, right? And to sort of look at this in even more detail, the dependence on this event becomes even clearer when instead of plotting the heat release rate as a function of time, let's now normalize it as a function of key events, right? So let's line up the heat release rate data as a function of all of the data points lined up for when the backrest ignites or when you get to your peak heat release rate, right? And compared to that sort of spaghetti plot of a bunch of different curves that we saw previously, now we start to see actually this is your median curve that's actually becoming characteristic of the individual curves that we see, right? And this shows that what's actually driving this process is the physical mechanisms of when you ignite the backrest, you now have a regime of upward flame spread. Therefore, you have a growing heat release rate up to the peak heat release rate, right? And so by tying these to physical occurrences, we can better contextualize the variation that we see in time, right? And so this is specifically for this chair, of course, right? But in theory, you could apply this to any fuel package, right? You could say if you can identify, for vehicle fires, let's say we can identify the key events that occur in every vehicle fire, and then we can understand that's what's causing variation in maybe some of our time resolved data that we might see, right? And once we have the data presented this way, you can sort of take the distribution of when these events occur. And in theory, if you wanted to, you could probabilistically recreate any design fire that you wanted. You'd be able to say, I'm going to vary when these events occur, and then that will shape the heat release rate, my output heat release rate curve, right? And again, that's just an idea that you could do to sort of look at not just this fuel package, but any fuel package where you can identify where the relevant key events occur and how you might be able to sort of leverage that at probabilistically recreating all the possible outcomes of that heat release rate curve. And that can apply to any fuel package, not just this chair. And so if you're interested in hearing more about the work that we did on the variability and heat release rate data in particular, you can check out our recent publication, Fire Technology, or you can listen to a podcast interview that I was that Wojciech Wierzyński was so kind to invite me to go on and have a chat with him about. And so there's much more information about this study in these two sources. But in terms of our discussion here, where does this stuff with this heat release rate variability leave us, right? Let's tie this all back to the idea of uncertainty, right? And so the idea of basing heat release rate off events, right? And the idea of like you can normalize things based upon events is really interesting in sort of contextualizing what are the physical drivers of the burning process, right? And how do we sort of contextualize some of that variability? But at the end of the day, right, as engineers, we need a heat release rate curve that's a function of time, right? Basically, we need to be able to put something into our calculations, right? And so, again, maybe this chair isn't necessarily going to be the basis for all of our design fires for the scenarios you might think of, but what does the insight of this variability tell us about the design fires that we might choose, right? So we've already discussed that taking an average through this is maybe not the way to go, right? Because you're going to very significantly underpredict the peak behaviors and the growth rates of any individual curve that you might see, right? You could maybe, from a completely different approach, you could envelope the entire thing, right? You could just take the maximum values, right? And you could do that in theory, right? But in doing so, you're no longer physically describing this particular fuel package, right? So by doing that, why even use this chair at all, right? You could just go to an assumed peak heat release rate. And the question of which of these design fires am I going to choose is a really interesting one, and I don't know if I have the best answer to that. So I'd be very interested in having this conversation, in the Q&A, or if anyone wants to keep chatting about this afterwards. But I think it's a really interesting question, right? Again, you could, like I said on the previous slide, you could probabilistically recreate, a million design fires based upon events and things like that. But I think it's also interesting. It's worth noting that choosing if the default is to choose the most conservative and fastest fire growth, right? So just taking the envelope. Are there scenarios in which this fire growth here, which is very gradual and very slow, is this the more onerous scenario in certain applications, right? Are there certain times in which this is actually a more hazardous condition? And maybe yes, maybe no, right? But by just taking the maximum, you're ignoring the fact that this was a possible outcome of this fuel package, right? So presenting the data as its entirety is important in showing that there is a range of possible outcomes. So depending on the analysis, one method might be more conservative than the other, right? So in terms of which one to choose, I don't know if I don't know if there is an answer to that, but I think the conclusion that I've sort of learned through this process is that I think the key takeaway is no matter what we choose, we need to be intentional and very explicit with why we've chosen what we've chosen as a design fire, right? The intentionality behind choosing this curve, I think, is the important part of this concept. And now tying it all back to where we started this presentation, right? So the reality is modeling the interactions between fire, people, and buildings is complex, right? And it is the role of the designer to identify these uncertainties and adequately mitigate any risks associated with those uncertainties. So ultimately, I think there's a couple takeaways, right? One, there is intrinsic variability in things like this heat release rate data, all right, or in the variability in the outputs of even simple things like correlations. Right? Recall the flashover correlations, right, where simple inputs and simple outputs, but if you go back to the original data set, there is a degree of variability on that, right? So there is intrinsic variability in the things that we do. Nothing's perfectly deterministic, and therefore we can account for these uncertainties. But an uncertainty isn't just sort of a question mark or something that we don't want to talk about. It is a tool by which we can then convey confidence in the outputs of our analysis, right? And so since there's variability on things like our inputs, right, there is going to be variability on our outputs. So articulating the variability in things like a heat release rate curve for a design fire goes a long way for quantifying what is our confidence in our outputs of something like a CFD model, for example. And unfortunately, we don't have a lot of databases for like large heat release rate experiments for things like this, and lots of repeats. And so hopefully it's something we can get more of in the future, just as an ability to articulate what kind of range of variability might we expect, right? And how does that variability start to change if we change ventilation conditions or the experimental configuration in which we're conducting these experiments. And so I think ultimately the thing to sort of end on is this idea of if we're using something like a design fire to size a smoke extraction system, right, or to do an ASET RSET analysis, right, tying back to the question of within the range of possible variation, right, does a small change in my heat release rate push my criterion from a passing criterion to a failing criterion, right? Is a reasonable change in my heat release rate going to make my smoke extraction system now fail in terms of the performance criteria? Right. So being able to articulate these things, I think, is what is meant by understanding these complexities and uncertainties in our kinds of analysis. Right. So tying it all back to where we started, there's tons of different bits of analysis that we might be able to do as fire engineers, but our ability to articulate uncertainty is a tool by which we can convey confidence, right? And at the end of the day, all models are wrong, but some are useful, right? We as fire engineers have to use tools at our disposal to protect people and property from fire, right? But I think the key aspect that hopefully we can do as a community is be able to identify and articulate our confidence in the outputs of any given analysis. So thank you for your attention. If anyone wants to continue these conversations offline, feel free to email me. I'm happy to discuss anytime. I'll leave some time for Q&A. I also want to give a quick shout out to the SFPE Foundation, who were very generous and sponsoring some of the funding that went to burning all those chairs. And so I'm very grateful for the SFPE Foundation for sponsoring that project. And I'll take any questions that you might have. Thank you.
Thanks, David. Really appreciate that. It's a very interesting subject, as we were speaking about before. I think it's an interest to anyone in the industry, and it's definitely going to make a difference for us going forward. If anyone's got any questions, stick them in the Q&A section now. We've got one in there at the moment, which is what are the main source references for determining design fire size?
That's a great. That's a really interesting question. I think on a simpler level, I mean, the way I would approach this too is what are the things that affect your heat release rate for design fire? If you have fuel packages, if that's sort of the place that you're going to start, there is a database. There's quite a large database. The NIST database is, if anyone isn't familiar with the NIST fire calorimetry database, there are tons of different complex fuel packages that have been burned under the NIST calorimeter, and they have data available on, you can download a CSV on all those heat release rate curves, right? So I think the first step is identifying sort of what are the ranges of heat release rates, growth rates, and things like that But in establishing a design fire, I think another important aspect is and something that we're working on with some of the chair study is if I change my experimental configurations, how does that change my heat release rate, for example, right? So we ran a bunch of experiments where we took the same chair, but we also ignited it differently, right? So we ignited it from a different spot, and it turns out your growth rates changed quite a bit. And so just getting an idea of if I am putting my fuel package in a room corner, right? Can we use actual experimental data to show how that affects the heat release rate? So the balance of choosing a characteristic heat release rate curve for a fuel package, but also getting an idea of what are the interactions that you have with different items in the room, with it relative to a wall. I mean, all those things, really complex questions that there are data out there for it, but I think there's a lot of work to be done to sort of tie that all together. And how does that inform our design fire, right? Because it is a really good question, and I hope to learn more in the years to come on how to answer that question even more.
Thanks, David. Another question from Laura here. He says, you run a lot of chair experiments to produce the curves which were presented. One can imagine other fuel packages where this might not be possible, such as larger or more complex or more expensive. Can you envision a way to do this process backwards to acknowledge the intrinsic variability in such fuel packages with a low amount of repetitions? Or is a large number of experiments always needed for each fuel package to adequately understand the variability we need for our heat release curves?
And that is an excellent question. So thank you for that question. I think this is something I've spent a lot of time thinking about because in a perfect world, uh, what would be nice with something like the chair data is to say, here are our error bars. Like, remember the flashover correlation? We were able to say, based on our regression analysis, these are our plus or minus error bars on the outputs of our analysis. It'd be really nice to take one data set with a lot of repeats of some fuel package and say, these are our error bars that are on all heat release rate curves, right? But the thing that stops us from doing that is the reality that, like I mentioned earlier, the heat release rate curve is just a manifestation of all the different events that occur throughout the experiment, or the process of this item burning, right? So in order to to actually say whether or not the variability you see in one fuel package will be the same that you see in another depends on how those different physical occurrences vary between those different fuel packages, right? A simple example of that is if you took the same chair, and we've seen this with other experiments, only done in sets of maybe two or three, but you can get an idea from this. You take the same chair that we burned here, and instead of using a Bunsen burner, I used a 15 kilowatt giant propane burner, right? Then all of a sudden those curves are going to start collapsing quite a bit because all of a sudden what's actually driving the process is this massive propane burner, right? And there are some standard tests out there where they're using 15, 20, 40, 100 kilowatt burners to test furniture. And it turns out you get a lot more repeatable data because the whole thing is driven by the burner. And so that's really interesting but that's going to change the process because that's the new physical driver driving the process, right? So what we were trying to go for was looking at the intrinsic variability of the progression of the fire kind of on its own, kind of independent from the ignition source, which is why we used a small ignition source. So that's just one simple example where unfortunately we can't apply the variability we might see for the small ignition source to a giant burner because you're going to have different physical drivers. And so the question comes down to, for your design fire, right? Which is the more realistic scenario? Which is the scenario that you want to go with, right? Is it a small wastebasket fire, or is it someone dousing a couch in petrol? But it comes down to I don't think unfortunately I don't think it'll ever be as simple as we can take the variability that we see in this fuel package and we can apply it to this one. And maybe if you can tie down all the physical drivers, you can get there. But I don't know if it'll ever be that simple. But I wish it was. I wish it was.
Thanks, David. A couple more questions. Instead of taking only one input of the heat release rate to CFD, why not consider the most three possible inputs of heat release rates to get more accurate output rather than relying on the average?
Yeah, that's great. I mean, I think one thing actually I meant to mention on one of those conclusion slides is on the extreme of choosing an average is you could put every single one of those curves into a CFD model, right? And so I think in doing so, I think there is benefit to that because what you could do is you could say instead of assuming one's going to be the most conservative output, just try them all because you might actually get a result in some sort of analysis that surprises your intuition a little bit, like, oh, actually this curve ended up being worse remotely to the structure and things like that. And so you could, yeah, in theory, you could just put multiple curves in, right? Again, going to the idea of you could also probabilistically recreate even curves that we didn't actually physically measure, but using the distributions of times and heat release rates, you could say create sort of pseudo curves of probabilistically recreated design fires. So that's another approach.
Perfect. Thank you, David. For me, and good to see you, Ian. Would you agree that one of the fundamental things that the designers need to understand is that all the fire engineering equations used are based on experiments and experimental? I'm guessing, not sure what you're trying to say after that, but data. And it is also has to be understood that experimental error is acceptable in a range of plus or minus 15 to 20%. So there's a range of 40% over which the answers may be acceptable.
That's a really interesting aspect too, and something that I wish I had time to go into, but I didn't go into detail on experimental measurement error, right? And so that is really important. So that's something that becomes very evident when you're in a lab trying to take measurements, right? It becomes very clear that there is a degree of uncertainty that doesn't just come from variability; it just comes from the fact that you can only get so close to actually measuring a phenomenon, right? And so, yes, it's true. All experimentation has some built-in measurement uncertainty as well. And I think the degree of uncertainty is also going to vary on your scale, on your equipment that you're using. Your uncertainties for sort of smaller scale correlations and using simple things like thermocouples might be different than the flashover correlations, where you have to use sort of coarser metrics to say like, oh, did this compartment actually flash over? But absolutely, and so I think that's something that we can as a community could probably be better about is explicitly stating what's our variability in terms of like statistical variation and what's our uncertainty in terms of measurement error. But absolutely, that's a whole nother facet to consider when we're using these equations, right? Because these were actual measured data.
Perfect. Thank you, David. That's all the questions, and we timed it perfectly because time's just about up now anyway. So thanks everyone for joining, and especially thank you to David for joining us at 2 to 3 a.m. that you are out in Australia at the moment. So it's very much appreciated. Like I said, a very interesting subject. This has been recorded, so we'll post it to our website and also on the YouTube channel for anyone that's interested. But again, thanks very much.